Next presentation is from the Bell. He is the CEO of the Bell company. And the Bell company, they only focus on the gravity casting and the low pressure. They manufacture the gravity GDC machine and the GDC mold and also casting too. Okay, let's start.
大家下午好。
Good afternoon, everyone.
关于半固态中立模具这一块，下午来主讲。
About the slurry GDC mold, I will make my presentation.
在主讲这个议题的时候，我先介绍一下我们公司。然后公司呢位于中国无锡，然后有1998年成立，公司有220人，占地面积在3万平。然后公司主要是致力于铝合金铸造装备、模具、低压铸造、重力铸造的生产和销售。然后主要产品是用在商用车上，是一汽解放动力的那个有色基地。2022年引进了GISS技术，应用到重力铸造这一块。23年成为GISS公司的半固态铸造模具的合作伙伴，然后为全球的客户提供半固态铸造模具装备的交钥匙工程。然后目前已经交付了超过60几个项目。
Okay, let me give a quick introduction. I think you can see that in English too. First, the company is in the location is in Wuxi area nearby the Shanghai, about 2 hours about, and established about 1998. And 2022, the collaboration with GISS together to make the GDC Mode 10K project for our global customers. And so far, they have delivered more than 60 modes together.
然后目前公司总部在无锡，主要是以研发为主。
And the headquarters is in Wuxi. The focus on the R&D and the CNC and logistics.
还有涉及到仓储物流。然后分公司有香港分公司，主要涉及到贸易。然后泰国分公司是现在正在装修，明年上半年可以对外来承接我们的服务，就是一个是模具制造这一块，然后装备制造，还有新品的一个试制。
And we have other subsidiary, one in Hong Kong, focused on the trade. It's a trade company. And also we set up the Bell Thailand. This nearby the GISS it's like a neighbor nearby us. And also in Bell Thailand, they focus on the gravity machine manufacture and mold manufacture and then sales and service and trial service in Thailand.
生产基地是位于中国安徽，然后我们的主要铸件场地，还有我们的模具生产制造、设备的生产制造。
And our production location is in Anhui province. And in this area, we do the GDC machine manufacture and mold manufacture, and also to do the LPDC and GDC casting production, mass production, big part.
这是我们安徽生产基地的几个生产线，这是我们的低压的铸造生产线，这是压铸的一个生产线，这是我们的重力的生产线，然后模具这一块的装配跟加工，然后这是我们提供了一个跟GISS合作的一个系统的，我们提供模具装备，然后还有自动化的一个集成一起。这是我们安徽的一个生产基地的一个试验基地。
And you can see the first one is they do the LPDC for big part. Second is HPDC small part, and then gravity casting, mold assembly, and they also provide the GISS GDC system. machine, mold, everything, and also they also have the GISS machine in their plant to make the GISS trial for some new mold trial.
这个是传统模具的一个交钥匙的一个流程。那我们从获取采购订单资料输入这一块，我们会做一个地分码的一个开模分析，然后做模流分析，然后涉及到砂芯结构跟模具金属模结构的一个设计，然后这是我们的制造环节，然后到我们的半固态模具的一个试制环节，然后产品检验到客户交样验证。
Yeah, this is a two-tone slurry GDC mold turnkey procedures. Yeah, first is from the get PO and then do the DFM analysis and numerical simulation and send and GDC mold design. Then mold manufacture and GISS mold trial, on-site trial, and then quality check after the deliver the sample and quality check if everything is okay and deliver.
我们从项目的交付周期，就平均在30天到45天。这个交付周期包括我们前期跟客户沟通交流这一块，还有一个我们的一个制造周期，还有一个验证周期。
Yeah, the average week from the PO to the deliver, this is including the communication with customer, the details, including this and including the on-site trial and the manufacture. Totally is about 30 to 40 days.
然后我会通过一个我们现在在生产的一个案例，来把模具设计这一块的概念跟大家陈述一下。我会从产品的基本信息、跟客户需求、跟特殊特性的要求来，这一块说起，然后从产品的结构分析，还有砂芯跟模具设计这一块。最后通过计算机辅助模拟，然后到我们的现场试制。
Yes, this is a basic flow from casting information input, and then casting structure analysis, sand core mold design, GDC mold design. After finish this, we do the simulation and the trial, GISS trial.
这是我们前期输入的一个产品的基本信息跟要求，然后材质是采用了356的一个合金，产品大小在160到87乘101，那平均背后是3.5个毫米，它的重量在0.8公斤，它最厚的地方是20.16。然后它需要通过空气车压在450千巴。
And this is a basic emission. Normally, it's an input of the casting information and material 356L and dimension, cast weight. The average thickness from 3.5 millimeter to 20.16 millimeter, and the pressure test about 450 kPa.
通过这个产品的热结分析，我们可以看出来，就是扩大部位在这个位置，还有这个位置，包括这个交界的几个位置。
Hello. OK. 返回去。And you can see the thickness analysis. You will see the some thick hotspot area.
然后这个是产品的内部结构，从产品的内部结构看到，我这边有一个气道芯，它是这是一个出口，然后还有一个出口是在这个位置，所以它整个产品内部结构是被一个砂芯包裹着的。
This is the casting structure analysis for this part. The challenge is a closed air flow. Closed air flow, you need to meet by the sand core. The sand core is surrounded the whole thing.
然后这一个蓝色的是一个香干净，但是它会影响到我们铸造过程中的一个冲洗捕收。
And this is the blue color. This is a steel insert. This insert will affect the flow and feeding too.
这个是我们内部结构的一个砂芯模具的一个设计。那从这个内部结构我们可以看出，它是通过4部分组成，包括我们这个刚才说到一个箱径是在砂芯上成型出来。
Yeah, this is a sand core design. You can see the assembly by 4 parts, and one part we have the steel insert will be manufactured, will be produced by the sand core during the sand core making, and then assembly together.
然后外膜金属膜设计这一块，从图片上大家可以看到，我们采用了一个镶嵌式的一个排气系统，然后还有一个保温的那个胶包，还有一个我们的采用的一个抽芯，其实是主要目的是为了我们这个产品结构的一个温度场。
And this is a outside GDC mold, steel mold design. And you can see here, this is like it's an insert. It's for venting, insert design for venting. And also here is a steel slides. Because this area is very thick, they use the steel to cooling faster to this hotspot area, and also use ceramic hopper.
这个抽芯结构其实我们是通过这个抽芯的温度差来解决我们尾端的一个热结的问题。
Yeah, this steel slide design is just for the cooling faster at the hotspot area.
然后模具的整个恒温系统是通过加热棒来加热，还有一个冷却的水冷系统来控制。
And also for the thermal balance, we use a electric heater and also some internal water cooling for some hot area.
这个是我们做的一个冲洗跟卷气的一个模拟。
Yeah, this is for the simulation for the air entrapment and solidification.
然后通过这个产品，我们可以看出这个产品是没有做那个排气相近，那这边是做的，所以它在模拟的过程中可以看到我们这个集中的一个卷气的位置。
This simulation, the 2 cavity, 1 cavity during simulation and the venting, and another one no venting, just show the differences.
这个是我们做了一个凝固模拟的一个顺序。其实我们看从模拟来看，里面这一段是被孤立的。
And during this is a solidification simulation. During solidification, you can see some areas still have some hot spot. The last solidification, you will have shrinkage. It's not.
Oh.
Yeah, you have some hot area, thick area.
这个模具设计好就是我们的一个制造过程，后面就是现在看到的我们这个结构就是我们现场做了一个模具的试制，然后通过我们前期模拟，然后数字仿真以后，通过现场的数据跟模拟数据重合的做了一个印证。
Yeah, this is an on-site trial. This is on-site trial, and based on the simulation and manufacture, and then make assembly and make castings to confirm.
这也是我们试制过程的几个关键的工艺过程的控制。
This is a key conditions during our trial.
通过半固态制浆技术，我们要控制的是一个温度， 一个就是在初始温度，在640度左右。
And first, we need to control the before GISS control the temperature. We set this 356L. We set about 640 Celsius.
所以我们在制浆结束以后，控制在635度。
We after GISS about 5 seconds, the temperature is about 635 Celsius.
那I356的它那个液相性是在615度左右。
And the liquidness of this alloy, 356 alloy, is about 615 Celsius.
所以我们在浇筑过程中，它的温度差会导致我们适应的真实性，就是因为要通过这个温度差，我们特意把我们的铸造装备在时间跟轻转角度做了一些改进，针对半固态这个冲型做了一些优化，跟传统的那个铸造机是有区别的。
We also do some optimization of the GDC machine to compensate and also to combine with the slurry GDC. It's a little differences.
模具温度控制在350度以上。
And mold temperature is higher than 350 Celsius.
它的温度主要是通过加热系统来控制，还有一个模具的浇筑的周期节奏来控制这个温度，然后还有一个我们的冷却系统。
The mold temperature is controlled by the heater and also the cycle time and also their cooling system together.
然后通过这个产品的印证，我们冲型的速度在4秒以内，然后它的凝固周期在120秒。
And also the increased tilt speed is it's about 4 seconds, and the solidification time 120 seconds.
然后我们通过GISS制浆的跟我们传统铝业来做了一个对比，也同样的工艺、同样的方式、同样的时间。那这个是我们半固态做的一个产品。从这个图片上可以看出，一个是720度浇筑的，其实它表面的一个流纹其实是砂芯的发气量，包括我们冲型有一个卷气，所以在这个平面它是没有排气。那这个产品也是通过它的一个冲型温度发气量，从这2个产品对比上，我们就可以看出，通过半固态的冲型，它的更稳，发气量会更少，因为它温度更低。
And they also compare the liquid castings and GISS, and from the surface, it is to be honest not too clear. And from the surface, we can see the air flow, and the surface airflow trick. We'll see that. And for the GISS, because of less turbulence, and also the key is casting temperature is lower. The sand burning have less gas. During your feeding, the sand will burning will get more gas. The lower casting temperature, less gas burning, less air. That's why the surface looks nice, looks brighter.
然后通过这张图片，我们可以看出，在冲型末端这个位置就是我们的一个冲型的末端。其实它的卷气跟凝固都会因为温度跟发气的量有很大的一个区别。这个是常规的铝业冲型，它的卷气，其实它这个地方形成了一个缩松、热缩或者憋气。
And compare that picture, this area is the last feeding area because the higher casting temperature, more gas, more sand, and more gas. You will entrap gas at that area. This area affects the cooling speed. Then you will have the surface shrinkage, and the surface cannot fill.
这个是我们内部质量用 CT 机做了相应的一个检测。从这边可以看出它内部缩松的一个质量问题。这个位置就是说我们刚才通过那个模拟 模拟可以看出这个地方是断层的，所以这个从常规履约来做的话，这个地方的一个疏松状态会比较严重，形成产品的一个不合格。那通过邦库肽，它的因为低温跟杀青的发气量会减缓这个问题。
And compare the before the solidification behavior, this area is the red area is hotspot area. There has shrinkage, but this is liquid. Compare the liquid. You can this area some shrinkage porosity, and because the loose GISS, this area is much better. Two reasons: one is the solidification. One is the solid particles affect the solidification behavior. Secondly, the sand core burning light gas to this area. That's why it's better.
然后这是我们工厂生产的3种工艺。那这个是我们没有在跟技术合作的时候，我们一直在生产的，也是一个1出2的，是通过传统重力铸造做的。这个是我们改进的，通过我们的低压铸造工艺来做的一个产品，也是1出2。然后这个是我们通过跟技术合作以后，通过邦固肽制浆技术做了一个工艺上的一些改变。然后从出品率来看，其实我们第一个我们的出品率是只有31.7%，然后一个周期是270秒。低压的一个出品率我们是做到了61.5%，但是我们的凝固时间跟周期是要300秒。邦固肽技术这一块，其实一个是温度下降了，还有一个我们的整体的重量也下降了，用铝量其实损耗也减少了，但是我们的出品率可以做到76.2%，凝固跟那个周期可以控制在120秒。
And this is a composition. And before they use liquid gravity counter pressure castings, liquid castings, the material yield is much lower, and the cycle time 270. And then they move to LPDC. Also compare the material yield increased, but cycle time longer, slightly longer. And then finally they try the GISS, and you can see the material yield increased about to 6%, and cycle time is much lower, 120 seconds.
这个是我们对我们的一个模具的加热跟周期，还有一个我们保温炉的一个能耗做了一个对比，然后通过这个对比，在光能耗这一块，我们可以降到20.8%。那制造周期这一块，其实我们跟从前面的数据可以看到，可以降到50%。
And here, this energy analysis from melting furnace and holding furnace, once they reduce, I think even Mark and Tommaso talk a lot about this energy saving. They calculate the real number for the user natural gas consumption reduced about 20%, only the melting.
然后我简单总结一下，邦固肽铸造模具设计的概念跟普通模具，其实液态的模具设计的类似。
Slurry mold design concept is similar as normal liquid GDC mold.
邦固肽模具设计需要短的冲洗时间，以避免冲洗不良的问题。
And slurry mold needs a shorter filling time to avoid non-filling issues.
翻转的速度快跟大胶口确保是大流量，它的冲洗速度会更短。
And we use a faster tilt speed and a bigger gate area to assure the less filling time to avoid non-filling issues.
然后邦固肽模具可以使用大的排气，一般的话，像排气我们可以做到20、50，然后一个它不容易产生飞边或者堵塞。
And for slurry mold, we can design bigger porous vents, not without a flash or block. For the GDC, the maximum is about 0.25 millimeter.
通过这些大排气，其实模具内部铸件的温度它也会迅速的会下降。
Because the big vents, they also slightly affect the mold temperature too, reduce mold temperature too.
半固态模具设计需要高的模具温度，以补偿流动性和补缩，所以对温控系统就要求非常高。
The slurry mold needs a hot die to compensate the fluidity and feeding. That's why you need to be carefully to control your thermal balance or mold temperature gradient.
然后从重力铸造来说，最后一条其实很重要，是模具涂料正确选用，对冲洗补缩是非常重要的。
In gravity cast, even in the gravity castings, a good ceramic coating is very important for filling and feeding too.
好，谢谢大家。
Thank you. Any questions? OK。给你个东西，给你个东西。Okay, the next one is from Tommaso. No, it's not that. Another one.
Okay, I change side. Me again. So, as mentioned by Yufeng, last year we announced that a simulation software was under development. This year I announced that the simulation software for GISS has been released. So this software is now onto the market and is installable, is usable by everyone who wants to use it. Okay, this slide is the same that I showed you this morning. And this is the justification why we develop a software specifically for GISS, because GISS is different. So you can use Magma, you can use Procast or Through 3D for reproducing, for simulating the processes, but their rayocasting module, they are not tailored, they are not fitting with GISS. They are reproducing and simulating the other kind of technologies, rayocasting and semi-solid technologies. The technology working between liquidus and solidus temperature. Since GISS is different, we work above the liquidus temperature, it was necessary to increase the accuracy of the simulation software to develop something different. CAS simulation software, of course, we start from the liquid module. This is the common interface that you can find all the parameters to fill in at the beginning of the simulation. CAS simulation for liquid is developed in Italy since 2011. So it's about 14 years that CAS exists for standard high-pressure die casting. So what we have developed now is the module for GISS. This is the same. This screenshot is showing the parameter input for the GISS module. There are some little differences, some different parameters that I will show you in detail very soon. I take the same sample that I show you this morning that I used for my cost model. The same part that I use for simulation, and I use this part for showing you the difference between liquid simulation and GISS simulations. So this part, as I told you, is a steering gear. Use the very standard alloy and die casting machine 1800 tons. The problem for this part at the beginning, it was porosity. There are 3 versions of this part. One part has been designed and developed with ventings, passive ventings. The second version is with vacuum, and the third is with the GISS. There were a general gas porosity, maybe in different areas, in different zone of the part. So this part is showing the cases where the gas porosity is the main issues. The second case study will be focused more on the shrinkage porosity, but now we are focusing on the gas porosity. So this is the sample of the first 2 versions with ventings, passive ventings, and with the two vacuum valves. Of course, I'm not here to show you the case study, but I take the opportunity to speak about the software. What I need to emphasize is the so-called dual phase. The software is dual phase. It means that we are simulating 2 fluids. One fluid is air and one fluid is metal. So metal is red and air is blue. And all the other colors, I mean the pink, the dark red, is where we have a very big combination of the 2 fluids together. So we are able to detect the flow front, the droplets that you have in the flow front, the spray effects. So filling done with 2 fluids, and both of them are modeled with their temperature-dependent physical properties, thermal and kinematic. What does it mean in terms of accuracy? There is no a sharp separation between metal and air. You know, in the simulation software, we work with the mesh. Every mesh has thousands and thousands of mesh cells. Every single mesh cell can be filled partially, both of the fluids. So you can have 99% of metal, 1% of air, 99.9% of metal, and 0.01% of air, and more, and more. So we can simulate the mixing of the small droplets inside an airstream or the small bubbles inside a metal flow. It's the same. It's the same. The result is that we have a high degree of accuracy in the determination of air entrapment. Why I'm highlighting this point? Because the famous magma or flow 3D, they are not dual phase. They are single phase. So they say, okay, we have air where there are no metal, but it's not the same. They are not, for example, ask to magma to calculate the air velocity to escape from a venting. They are not able to do because air is not a fluid inside their calculation engine. So this makes possible to show the only air. The pink one is air 30%. It means that the cells with the 30% of the volume filled up by air, but of course this 30% is user-defined, so I can show 30%, 20%, 40% is up to us. And also we can detect very accurately the amount, the volume of entrapped air, for the reason that we don't need to have a very small mesh size to detect a very small teeny gas porosity. For example, in this case, I'm showing 1% of volume filled by air at the end of the filling time. And this percentage, of course, can be even lower. So we can detect a very, very small amount of gas porosity at the end of the filling time. This is 5%. Of course, it's like when you use a a microscope, you use a different magnification. If you use a 1%, you detect a very small gas porosity. If you use 5%, you see bigger bubbles. Let me speak very roughly. So, using a vacuum, the foundry has partially fixed the problem because in some areas the situation was better, but in other part of the, like this, there is still gas porosity. So even with two vacuum valves, and believe me, we are vacuum machine producer. We provide the vacuum valve, so we spent a lot of time, but it was not possible to get a fully compliant part, even though with the vacuum system. Now, I introduce you to GISS, to the GISS simulation software. I told you there are some different parameters to control and to input. First of all, the kind of alloy, of course, alloy are the same for liquid and for GISS, but now it's possible to add the liquidus and the solidus temperature. For GISS, it's very important to immediately to have a look and to know which is, above all, which is the liquidus temperature. Because when we try GISS, the first thing that we do is to find the liquidus temperature. And this liquidus temperature can be changed by the user. So we have a database with all the alloys, with all the liquidus and solidus temperatures, but if requested, if the user wants to do it, can be user-defined, can be changed by the user. Because in the testing the foundry is not exactly the same. It's not 509, maybe, yes, 589, but maybe 591, can be. Second, GISS time, the number of seconds that the probe is in the ladle. This is later I will show you that the software is consistent, so it's change the results in relations. Are 5 up to 15 degrees higher than. It's not working. Usually we are 5 up to 15 degrees higher than liquidus in production. And also we can virtually understand what happens if we use this temperature. And last, the pouring delay time. So it's the time from GISS treatment to pouring. And also this affects a lot, can affect a lot the final result. On the basis of this, the software has inside a model about relationship between input parameters, viscosity curve. First of all, input parameters, calculated, estimated solid fraction, and viscosity curve. So on the basis of this, can say, okay, probably with this alloy and with those parameters, we start with 3% of solid fraction. And at the end of the filling, because it's a dynamic process, we can reach 10%, 15%. Of course, it's a theoretical and numerical calculation. It's not yet a simulation. So now I'm showing, of course, with GISS, the foundry has eliminated ventings and vacuum and channels. So we have only the standard overflows. And what I want you to pay attention is the different kind of flow behavior, of flow. You see, the flow behavior is much less turbulent and more similar to plastics, to injection molding. For example, you look on the left, that you still have air behind the flow front when the metal is moving inside the part, but air is everywhere for the turbulence of the process. When the flow is laminar, you have air only in front of your flow front, so not behind. You have not entrapped air behind the flow front. So this is the same. You can appreciate where the gas is evacuated through the overflows. Also importantly, the velocity calculation. Because of this, in comparison with liquid, the metal velocity is lower than the liquid one. So finally, of course, because on the contrary, I would have not shown you. Of course, the results are good. So we have not fully eliminated the gas porosity, but certainly the part has been improved through the use of the technology. But my purpose is to show you the software. So for example, I show you the consistency with the different parameters. Here is a comparison between GISS time 10 seconds, GISS time 2 seconds. What I want you to pay attention, that with 2 seconds in this case, the flow is more similar to liquid. Maybe here is also more evident. Yes, it's more evident. You see by the velocity colors. And also at the end, the final gas porosity detection in comparison with 10 seconds, 2 seconds. So that's the reason that we say that this simulation tool can be helpful for the GISS user, but also for the people not still using GISS, for understanding the potential benefits of the GISS application to your own part, because you can also evaluate which are the best parameter to apply and which are the potential advantage can be achievable. Another point is the pouring delay time. Pouring delay time is the time that we spent from the GISS treatment and the pouring. So in this case, now the probe is going up. Okay. And we have 1, 2, 3, 4, 5, 6, 7, approximately. We have 7 seconds between GISS and pouring. What's the point? The point is that if this time is too long, the solid particles remelt. So we lose all the good effect of GISS. So in this case, of course, is exaggerated, but if pouring delay time, if we wait for 20 seconds from GISS to pouring, the the simulation show that in the second case, 20 seconds is exactly the same as for liquid. Okay, and you can see the speed. And the same for the detection of the gas porosity. Another point, GISS temperature. So the temperature of the metal temperature when the probe is inside the ladle is very interesting, because if we set 590 degrees, the simulation show that we are not able to fill completely the cavity. So we have a misrun. We stop before, as you can see. It means that the metal freeze is too solid, becomes solid before completing the filling. And also you see it is very, very slow for this, because it's too solidified. Another point, what happens if I use different alloy? I compare different alloy. What I want to show, that if the silicon content of our alloy is high, or higher than 10% or 11%, a longest time is useless, completely useless, because the creation of the solid particles is in the primary alpha. Maybe okay, it's more metallurgical, this kind of information, but it's not in the eutectic. So after 2 seconds or 5 seconds, it's completely useless to continue to use the probe inside the ladle, because I'm not creating anything in the primary alpha. And the software is able to reproduce this case. The final result is that we have more gas porosity with a longer GISS time with higher silicon content. Second case study. This case study is focused on the shrinkage. So this is the same. Maybe some of you were here last year, and I show this is the same case study. I have just updated some results. Is a compressor for a motorcycle. Okay. The kind of defect on the microscope that with liquid, and here is the filling pattern. You see very different, much less turbulent, and much more laminar. Maybe you can appreciate. And this is the air. Yeah. From the side of the gas porosity, we have an improvement, but probably not so meaningful. There are still a good amount of air also in using GISS. But if we simulate the solidification, this is the different solidification pattern for GISS and for liquid. We start, of course, from different values, look to the scale. The scale from GISS start from 597. And this is the liquid fraction over the time. Of course, take care of the time is different. But if I stop, at the same time, after 5 seconds, and if we look inside, not on the surface, if we look inside of the part, this is a section of the part. In case of liquid, we still have 100% of liquid metal inside. After 5% with GISS, of course, because we start from a much lower temperature, the liquid fraction is less than 30%. So this is really meaningful. And also look to the cooling rate. If you look to the solidification, you see there are 2 blue spots exactly where we don't want to see them, because the cooling rate is different because of this. And the final result is that from the X-ray, the kind of issue has been improved and has been fixed. So not so much better for gas porosity, but better for shrinkage porosity. So summary about the software. The software is composed of multiple modules. One module is about the feasibility analysis, not yet simulation. We have 3 and now 4 modules of simulation. One is the more specifically for the die designers. So a fast evaluation of the runner's efficiency. So is a calculation that can take few minutes, but in a few minutes you can see if your runners is working well, if your ingates are enough or not. The simulation for the filling and solidification and full die I mean all the thermal part, thermal cycle, the thermal cycle, so with the cooling channels, with all this line, so the thermal balance of the mold. And now the slurry filling and solidification simulation. Of course, this kind of simulation take more time. I mean computer time. So they are fast to prepare. I mean minutes. But the calculation times depend on the computer, but they are hours of calculation. So the first module is the castle mind. We have the capability to show the PIQ2 diagram. And also the castle mind express the suggestion in very natural language. So you can tell you, okay, maybe your gate is oversized, undersized, your plunger is too big, too small, is increase the first phase velocity, decrease the slow phase, so can be many different kind of suggestions. This is not yet a simulation in terms of fluid dynamic, but it's useless to run a simulation that take maybe 4 hours, 8 hours, when you can know in advance with a calculation of 5 minutes that you have a very small gate, for example. Of course, if you run a simulation, a filling simulation, you will find that the gate is small, but it's not necessary to run a full simulation to know this. And also, the software suggests the theoretical and the optimized parameters. For example, the parameters for the switch point from first phase to second phase, from second phase to third phase, and also other parameters. That parameters are good for the foundry, but they are excellent for the simulation, because one of the problems of the simulation, filling and solidification, and is many times you run the simulation when you are still in the office, the die is not done. So you have to invent the parameters from the scratch, and it can be very wrong or can be very far from the reality. The software incorporates the die casting machine performances, so you have to select your die casting machine, and on the basis you select the right alloy, and you can have reasonable. They are not correct 100%, but they are reasonable. It means that can be used for the simulation, for the filling and the solidification simulation. Also incorporates the capability to calculate in terms of estimated entrapped air if you use chill vents, if you vacuum, if you use nothing. So how much is the estimated entrapped air in terms of millimeter cubes for the part with different solutions? As I told you, okay, here there is a video. Okay, we can simulate the short sleeve filling and the runners very fast in order to understand if they are well designed or not. So also in this case, it's not necessary to run a complete filling simulation to evaluate the runner's efficiency. Evaluation in terms of velocity, in terms of kinetic energy, or entrapped air inside the runners. Okay, back to the point that I touched before, difference in the dual phase simulation, the capability to take care of the air back pressure, and see different visualization, no venting, chill vents, and vacuum. And it's very easy to see that the dual phase effect on the simulation, and also about the porosity. Okay, the final results is that, okay, we spent a lot of time to check the accuracy of the software. So in the software, the test phase is very important, and we compare many times the software results with the X-rays, with the casting results. It's a very huge job to do. So, nothing to add. What we provide? We provide both simulation service and the software license. Simulation service can be just simulate for you, for your customer, for your partners, the analysis of the mold, or we can sell the permanent software license, including 1 year of maintenance. Since we are promoting now the software, and of course it's definitely right that people want to try, of course we can provide a trial license for a limited number of time, but now we are pushing for one set of simulation analysis for free. So you can send me the data, the geometry of your mold, and the process parameters, and what we can do is to make a simulation with liquid and one with GISS, and in order to show you exactly on your own part, not theoretically, which kind of differences there are and which kind of benefits you can get from using GISS. So we are, of course, we expect to have some job to do, but we really believe that is the only right thing to do, is to let you appreciate the capability of GISS and the capability of the software. Thank you.
Okay. But if you have any questions, you can ask Tommaso later. Oh, yeah.
I want to refer for you some idea, my interest. You can make it a semi-solid clay cast iron engine box. You can make it a semi-solid process for clay cast iron engine box.
For engine block?
Yes.
Yes, of course. The simulation can simulate everything. So yes, and also engine block is one of the kind of.
I want to be construct for new engine block high performance by semi-solid cast iron. You can
Cast
make it.
iron.
Yes,
no,
right.
no. Well, this is aluminum.
Oh, okay.
Aluminum, high pressure the casting aluminum. So since we believe that high pressure the casting is very different from gravity, from other, it's impossible to use the same software engine for different, different. So no, we have not developed for cast iron and we are not going to do it.
Too easy to construct new engine block compacted graphite by cast process.
Sorry. Maybe again,
Thank you very much.
Okay. Thank you.
Okay, just to verify again, we are focusing more on aluminum casting, and I think it's the future for EV and high efficiency for lightweight components. And also we see a lot of cost savings when we apply to aluminum, because aluminum has a lot of problems. One of the most difficult alloy to cast, as we mentioned together. And the trend in the industry right now are focusing for passenger cars as two alloys, two metals, magnesium and aluminum. So far, only these two alloys or metals. So we will focus more with Tommaso on aluminum, and also the database for different metal and alloy are very different and very difficult for Tommaso to get all this database, and we need to verify everything. So I think it would be a great example and case study to start somewhere, and you can contact Tommaso directly or Yufeng. We will work together on this. Okay, please, we have another gift for you. Because you have spoken 2 times, you get 2 gifts. Thank you.
Oh, thank you. Thank you. Thank you.
Thank you. So it has been a long, long day and many days for some of you. And as you can see, Yufeng and I are trying to speak less and less, and we are getting more partners to speak more and more. So hopefully the next GISS Forum next year, we will get some of you or many of you to speak more, and we will share this. And as you see, we have the same attitude or the same mission. We want to save the planet. We want to share all of this technology so everyone is using it, so that we can reduce the carbon footprint. And climate change problems is the key problem that we're dealing with together. So our team will be happy to work with everyone, and we may even form coalition in different countries. We start with Thailand, China, India, US, Europe. So we have advisors working with us. I cannot alone work on this. Yufeng cannot. We have Edward working with us at Vice President over there, as you may not know. And we just got John to work on the aerospace and the UK market. Thank you very much for coming. So next year, we have Mark starting to help us a lot. And he said he will order 50 bags for me. Just kidding. So thank you for coming and enjoy your trip in Thailand, and hope to see you next year again in Bangkok. Thank you. Thank you. See you. Have a good trip.
แล้วแต่พี่ยุ้ยเรียกตัวเลยครับ
Yeah, I'll do it right now.
าพที่ขึ้นอยู่ตรงเนี้ยเครื่องกู
ก็สวอปมันคือต้องการเกรดสีไม่ต้องมีใช่ไหมหรือเครื่องการเจ็ดไม่มีหรอเอาเขาเก็บไปแล้วเหรอ
เก็บไปแล้วเก็บตั้งนานแล้ว
แล้วอันนี้เครื่องใคร
ฮะเครื่องออฟฟิศ
มันมีไฟล์ปะล่ะ
ไฟล์แน่หรอไม่มี
จบ
เครื่องนี้
จบ
ไม่รู้
ทำไมไม่ได้ปิดอ่ะ
ไม่ได้ปิดมิวไว้ก็ได้
พี่กบอยากเข้าไปด้วยแล้วค่ะพี่กบอยากเข้าด้วยคุณบอวิ่งมาไม่แต่ต้อง
ต้องรื้อนี่ครับให้ครับคอมของออฟฟิศวางไว้ให้ที่โต๊ะแล้วนะครับได้ครับเดี๋ยวไปเก็บตรงครับเดี๋ยวจะถ่ายรีวิวตอนรื้อไลฟ์ตอนรื้อเนี่ยตั้งกล้องงั้นแหละไลฟ์สดตอนรื้ออันนี้จบแล้ว